And the idea about algebraic geometry is that very often you work over a base. And so, for example, for us, spec C is the base. And so a variety X over C really means a morphism from X into spec C. And so what happens is that a lot of times you want a more general base. So you will, instead of working with just schemes over spec C, you'll work with schemes over Y. And so what you want is you want often relative versions. It's relative to a base. So you need relative versions of basic notions. An example is when we talk about complete varieties, and we saw some nice examples of complete varieties both in the lecture and in the homework. When you make it relative, we have a morphism, and what do we call the morphism? It's the relative version of complete. It's not projective. Proper. And that's the whole point. And it turns out that in a very unimaginative way, the relative version of a projective variety is a projective morphism. And so basically, you need to define what it means for a morphism to be projective. Now remember, when you have this proper map, Y could be all sorts of crazy stuff. It might not be remotely compact. Similarly right here, the base might not be remotely projective. It might be all, it might be all sorts of strange stuff. It's really sort of the fibers that you're interested about. And if you look at Hartshorne, on page 103, he gives a definition of projective variety. And it's sort of a nice one that sort of makes sense, that when you have a commutative diagram, well, first of all, in a projective variety, you just embed it into projective space. What's the relative version of projective space? Well, it's pretty obviously Pn cross Y. And then you just have that. And so what you want to do is you want to map into a relative projective space. You simply want a closed embedding. But it turns out this is actually not a really fully general definition. It turns out this definition works when Y is quasi-projective. And remember, a quasi-projective variety is something that's an open subset of a projective variety. So this is a class of variety that includes, It includes projective varieties, includes affine varieties, it includes, for example, like if I take a affine space minus the origin, that's the guy we built projective space out of, that's not affine. It's also not, and this is assuming that n is bigger than 1, so it's not affine and it's not projective, but it's perfectly good quasi-projective. But it turns out that in fully generality, this is, if y is a really nasty variety, this is just a slightly too restrictive notion. So you need a definition, so you need a general definition. And here's the general definition. So there's sort of a local aspect and a global aspect to being a projective variety. So the local aspect is that locally it looks like that. So Y has an open cover UI such that when I look at F inverse of UI, so when I look at this map over UI, then I get a commutative diagram. This is closed and this commutes. But there's also a global object, because a projective really says that there's some stuff that sort of makes all this hang together in a reasonable way. And the global object, or the global aspect, there exists a line bundle script L on X. So basically X has a line bundle, so something on all of X, not just on these pieces of X. Let me call this star sub I, because I get one of these for every index I in my open cover, such that star sub I, because you see right here, what this is saying is that these guys, an embedding here basically says there's going to be some line bundle that gives this kind of picture. And the point is I want this picture that actually comes from sections of L. But I have permission to use different sections of L for different I's. So to me, this is not a very intuitive definition. I had to open up EGA and read it. And I said, well, if Grothendieck thinks that's the definition, I agree with, I'll trust Grothendieck. But it turns out it does have the right kind of properties. So let me give you a couple of properties. So first of all, this is projective. And also, composition of two projective morphisms is projective. A closed embedding is a projective morphism. The base change of a projective is projective. And the final one is that any projective morphism is proper. And you can actually see the proof of that, because remember, we stated earlier that this map we already know is proper. And then the base change of a proper map is proper, so this guy is proper. And then proper, and that's a closed embedding is proper, composition of proper is proper, so that guy's proper. And proper has the property of being local on the base, and therefore that makes this guy proper. So the proof of this is just understanding sort of the modern algebraic geometry. And one comment is that proper is local on the base. Namely, if you give me a morphism in an open cover such that these guys are proper, then that guy is proper. So that's what local on the base means. But it turns out projective is not. And that's because of this global aspect right here. That just because I sort of have some line bundles on these pieces, they might not glue together. Okay, so that's all I want to say about projective. And what we're going to do tomorrow is try to figure out when is a toric morphism projective. Because earlier we talked about when a toric morphism is proper. So we actually have a properness criterion for toric morphisms. And so we know what that means. That was something in terms of how the support behaved. But then we saw today that projective required a certain kind of ampleness. It required ampleness that required a support function with a convexity property. So we have to meld sort of the thing we have for proper together with this convexity. So we need sort of a relative version of convexity. And that's what we'll do tomorrow in the first hour when we talk about projective morphisms. So the next thing is this funky notion of reflexive sheaf. And the idea is that when we have a Cartier divisor, and Hal talked about how when you look at this, this is a line bundle which equals a rank 1 locally free sheaf. And of course that's contained in the larger universe of locally free sheaves of ranks 1, 2, 3, 4, and so on. So the idea is we have a really good sheaf understanding, and in modern algebraic geometry, sheaves are pretty important. So Cartier divisors are definitely important objects, but a lot of people really think of them in terms of the sheaves that come from them, and the sheaves are these really nice. And but then when we have a Vey divisor, we certainly have the sheaf, but it might not be a line bundle. And so the question is, what is it? And of course you could say, David, isn't it a sheaf that comes from a Vey divisor? And the answer is yes, it's a sheaf that comes from a Vey divisor, but the question is, can you give an intrinsic characterization? Because that's actually all what Hal did here. He really showed you, how you can talk about this locally free sheaf in a very abstract way, and then you prove a theorem that says that characterizes Cartier divisor. So what's the thing that happens here? And so let me just remind you a tiny bit about sort of how sheaves work. So take a take one of our nice commutative rings with 1, take a finitely generated R module, and then we get this sheaf that we'll just call M tilde. In a sheaf, I have to, basically I have to tell you what it is. So, we have, so this is going to be on X equals spec R. So the question is, what is the sheaf? And the idea is that this is not all open sets. But the idea is if I take a non-zero element of R, and just to make life simple, so then I just take a localization. So, in a sense, I'm just looking, and remember, this is basically saying, this is the open subset where F is non-zero. So we get this open subset, and then the point is that the values of this sheaf on this open set, well, the point is I can localize rings, I can localize modules, so it's just that. And then the crucial thing is that when you look at the global sections of this, these are the global sections on X, you just get back the M you started with. And so all it is sort of a very nice, so basically it's you have a finitely generated R module, and you sort of have a whole family of them, sort of one on every open set. And this is what's called a coherent sheaf. So basically, locally it means it looks like a finitely generated R module. Now if I have so here I'll just let F be a coherent sheaf. And then stuff you do with modules you can do with sheaves. So like for example, you can take HOM. So, and notice that one thing I should mention is that this is an RF module. And of course RF are the global the sections of, there's basically the structure sections over XF. And so the idea is that we have this sheaf of, and so this is basically a coherent sheaf of OX modules. So I can take its dual, but this isn't just the set HOM, this is the sheaf HOM. So basically on every open set, I would sort of look at the localized things, and if X is an abstract variety, this all fits together. So this is a perfectly good sheaf. And so this is the dual of F. So it's got an F with sort of the dual thing. And then you have a natural map from F into its double dual. And then the definition is that F is reflexive if this guy is an isomorphism. And so it turns out that one simple example I have locally free of finite rank. Well, it means locally it just looks like that. When I take the dual, it still looks like that. When I take the double dual, it still looks like that. And that makes it easy to check that this map is actually an isomorphism. So these guys are reflexive. And so basically the category of reflexive sheaves includes all the sheaves of finite rank. This. And I should also point out is that the rank of F, so what on earth is the rank of F? And so this is, again, this is coherent on X normal. And there's a couple of ways to think about what's going on. And the way I like to think about what's going on is you simply, let's just think about what's going on an affine open piece. Because you want to think, rank is sort of done generically. Suppose this is spec R. And then let's let K be the field of fractions of R. And that's just, you know, that's just the function field of X. And then F will be, this is a finitely generated R module. And so then what you can do is I can take M, so here I'm giving the very naive notion, you take M, you tensor it over R with K, M is finitely generated over R, the tensor is finitely generated over K, that's called the finite dimensional vector space. And so the dimension over K is the rank of F. A much more sophisticated notion would be if you really use the scheme theory, it's simply you look at the stalk over the generic point of X. And that's basically what I did here. So I can talk about the rank of one of these guys the same way I can do here. And this is, I can talk about the rank of any coherent sheaf. It doesn't have to be reflexive. And so here's the first proposition. So this is proposition 8.0.1. F is coherent on X. So the first thing is that the dual and the double dual are reflexive. And of course, once you prove the dual is reflexive, that's automatically reflexive. So the idea is that a sheaf can have a lot of gunk, but this process of sort of mapping into the structure sheaf, take the dual, like gets rid of some of the gunk, so it makes it nicer. But still, computing these kinds of things is not easy. So what happens is, suppose that I have an open set of X with two properties. The first property is that the codimension is greater than or equal to 2. So basically I'm throwing away some pretty small stuff. Because the higher the codimension, that means the smaller the dimension of the stuff I'm throwing away. And then also let's suppose that on this open set, script F is locally free. Then it turns out in this case, you can actually compute the double dual just by taking what's called the push forward. So just J lower star of F restricted to U. And the point is that's locally free. And this is something that you can compute sometimes without too much difficulty. So that's saying that in certain cases, this is not bad. If what we're going to do is that in some situations, we're going to have a sheaf that we sort of like, but it's yucky, and we want to make it nice. We'll make it reflexive by this, so I want to replace it with that. And but to actually compute it, we'll use this technology right here. So this is and we'll see that there's situations where this is exactly the setup we want, especially when we deal with differentials. And in fact, let me actually give an example that has that. So this is a little preview of the third section of my talk. So you can actually talk about P-forms like in differential geometry, 1 forms, 2 forms, n forms, stuff like that. And it turns out that, and I'm going to define this in about 10 minutes. And it turns out that this is locally free of rank n choose P, where n is the dimension of x. And this is when x is smooth. So in the smooth case, and that's certainly true when you do P-forms in differential geometry, that you get a nice bunch of P-forms, and that's exactly the rank that you expect. But it turns out that it's just really awful in general. And so if you're trying to do, for example, when you do Hodge theory and things like that, you actually need, in fact, in Hodge theory, you need HP of x. For a smooth manifold, this is sheaf cohomology. Hal's going to tell you about that on Wednesday. And so these are the so-called Hodge numbers, so they're really important. And yet, this really is only good when x is smooth. So what do you do? So here's the definition that I'm going to give. So remember x is normal. That implies that the smooth locus is pretty big. So it's an open set. And it has this codimension condition. Because basically in a normal variety, the singular locus has codimension at least 2. And so then what we get is that, so we're going to define what are called the Zariski P-forms. So we're going to put a hat. So that's the gadget that we're actually going to use. And what it is, it's going to be, like I say, we really like this, but it's yucky. Let's make it reflexive. So I do the thing to make it reflexive. And so I take the double dual. But I'm in exactly the situation where I can do this, because let's call this inclusion J. I can take J lower star of, that's a P there. And of course, when I take this and restrict it to U, I just get the P-forms here. And of course, this is locally free, because U0 is smooth. And so we actually have a good way. And so these are the so-called Zariski P-forms. And so when you try to do sort of P-forms, differential forms in algebraic geometry, when singularities enter the picture, this is typically what people use. Yeah? So here? Oh yeah, so sorry. Yeah, so I take the yucky thing and I make it reflexive. And the point is that this is a reflexive sheaf. And it's a reflexive sheaf of rank n choose P, because right here it has n choose P, so there's a Zariski point. That'll be the dimension that you get. Now comes the way to really fit this all together. Because remember, I can now answer this question. It's not a line bundle, what is it? And so the proposition is very nice. This is Theorem 8.0.4. And so let's take L, a coherent sheaf on X, and X is our usual normal variety. Then L is reflexive of rank 1 if and only if L is isomorphic to OX of D for some V divisor. And so what we get right here is exactly the OX of D's. They are on the nose the reflexive sheaves of rank 1. Now the final thing I want to say about reflexive sheaves is that there's stuff you do to them. Because after all, I already talked about the dual. The other thing you do to sheaves is you take their tensor product. So let's take some V divisors. Well then, one thing that could happen is that you could talk about what it means for two V divisors to be linearly equivalent. That's, you know, a basic thing we've been talking about quite a lot.
I think I broke it all.
I know, you broke them all. Trying to find one longer than 1/4 inch. And then of course the other thing is that, you know, when I have sheaves, you can talk about just what it means for two sheaves to be isomorphic as sheaves. And the point is, this is an if and only if. And then so there, you know, what's happening with our basic equivalence relation of V divisors, that just turns into isomorphism of sheaves. So instead of you know, the class group really becomes sort of the isomorphism classes of reflexive sheaves of rank 1. But then of course you get OX of minus D. And so that's sort of doing the negative from the divisor point of view. And then the other thing you can do is of course just take the dual. And if you think about it, the dual of a reflexive sheaf is reflexive. And so that means this is O of something, and it's actually that. So that's very nice. Now it gets a little trickier when I want to add sheaves. Because, you know, I can take OX of D tensor over OX of E. So you're given two sheaves, I take their tensor product. Turns out there's a completely canonical map from that into that. So I have this canonically defined map. It's an isomorphism in the Cartier case. You know, it's a line bundle, that's a line bundle. The tensor product is going to be a line bundle. But maybe not in the V case. So the tensor product of reflexive sheaves need not be reflexive. So it's a little trickier than that. And so rather what you get, so can anybody guess what I'm going to do? How you'll be pleased to know I broke the chalk. I'm just getting it ready for you in the morning. Although actually it's me in the morning. So anyway, so this sheaf is bad. How do I make it good? double dual. And it turns out that what happens if you take, see the double dual here does nothing. And so what you get is that when you take the double dual, then you get that. And what that means is you can actually interpret the class group now purely in sheaf theoretic terms. It's basically, it's a, isomorphism classes of reflexive sheaves of rank 1. The identity element is just OX. And this is what the inverse is, and here's the product. Take the tensor product and double dual it. Okay, so I'm 2/3 of the way done. So I am not going to take a full hour, so I think that's okay with you. Now let's do differentials. And I'll just, do it some really basic stuff. Just P forms just on affine space. And so what we get is there is a sheaf of P forms. So I get omega 1 C, so it's actually a sheaf. But of course, what is, this is a sheaf of one forms. What does a one form look like? Well, it looks like basically, my coordinates dxi with some coefficients, and if it's going to be a nice one form, they should just be regular functions. And so this is really just going to be the direct sum of O, the structure sheaf of Cn times dxi. I goes from 1 to n. So that's basically what you want. And of course, the basic operation you do is you take a function, polynomial, and then you get a one form just in the usual way. And that basically, if you think about it, that's a global section of this guy. And then of course you get P forms just by taking the sort of sheaf version of a wedge product. And so, that's just the usual thing. Well, it'll be a big direct sum. Now it's, it's the structure sheaf of Cn, times dxi1, wedge dxin, or IP for all I1 up to IP. And so here's our nice locally free sheaf of the appropriate rank. So like I say, in this case, the algebraic theory is glorious. Now, how do we do it in general? And what I'll do is I'll tell you about how to do it in the affine case, and then it just patches together. So X is spec R. So what we call omega 1 of X, what's going to be a sheaf on spec R, so that's going to come from this game. So there's basically, I'm going to cough up some finitely generated R module and tilde it. So this is going to be, in fact, I'll call it omega 1. It'll be R over C, because we're doing differential forms over C. And I just, so this is going to be an R module that I just turn into a sheaf. And what is this guy? These are called Kähler differentials. And the answer is, what I want to be able to do is this. So basically I want to take something in R and I want to be able to form df. So I said, okay, let's do that. So I'll just take a humongous direct sum. So this is a ginormous, free module. I mean, if R is, over the complex numbers, this is uncountable direct sum. So this is, and so there got to be some relations. And, well, I mean, the obvious ones, so the big relations are, well, you want the D operator to be, linear. So we throw in that. We want, we want stuff to work nicely with the constants. So, it's the constant multiple rule. The derivative of a constant times a function is the constant times the derivative. And then what's the other rule we want? The Leibniz rule. So, I want D of Fg. And of course here, what this means is, I want it generated by all of these, and all of those. So, I have this humongous direct sum modded out by this incredibly huge thing. And so the quotient, whatever the hell it is, that's the right thing. And it has the correct universal properties. And it turns out that when R is this guy, turns out that omega 1 of R over C really is just the direct sum of R dxi. So at least in this case, it turns into the right thing. And then, of course, in general, for the non-affine, and the thing is, this has very good functorial properties. It behaves well under localization and all sorts of other stuff like that. And if X is a union of affines, then we get omega 1 of X restricted to UI is just going to be omega 1 of UI. And, just that. And again, because of the functorial properties of this actually patches and I actually get a nice coherent sheaf of the kind we want. We're getting pretty close to the end. And then the theorem, so the question is, I have, I have this sheaf, and when is it nice? And of course, here, this is a free R module. When I tilde it, I get a locally free coherent sheaf. And so the question is, in general, when is this locally free? And it turns out that that's if and only if X is smooth. So basically this guy is really nice in the smooth case. Beyond that, it's pretty nasty. And then of course to finish off, the general P, omega 1, omega P of X is just the wedge of that guy, and this is locally free of rank n choose P. Again, n is the dimension of X. When X smooth of dimension n. And then what happens is that this can be dreadful. When I take the wedge of something dreadful, I get something P times dreadful. So we got to make it nice. It's pretty obvious how to make it nice. The Zariski P forms. So this is I've already done, so I'll do this super fast. that I just, you take the double dual and do this, and so this is reflexive. Now the case that is actually generally interesting, and the case that is, some of this is, like I say, relative to various bits of Hodge theory and stuff. The case that is really directly relevant to us is the case of N-forms. And we often call it with a little, so that's the Greek letter omega, small lowercase omega. So this is the uppercase omega. So it's the Zariski N-forms there. And so this is reflexive of rank n choose n, which is 1. And if it's reflexive of rank 1, what does it come from? Comes from a V divisor. And what do we call that V divisor? And that's the so this is the canonical sheaf. And it comes from a V divisor. That's the canonical divisor. And basically, Kx is a big deal. Not just in toric geometry, but in general. And just to finish off, let me give one example for those of you who have seen something about Riemann surfaces. So a smooth projective curve of genus G. It has a canonical divisor. In fact, in this case, of course, it's Cartier because the variety is smooth. Does anybody remember what the degree of the canonical divisor is? It's a 2G minus 2. And it turns out that when you classify algebraic curves, they basically come in 3 flavors. There's the genus 0 curves. They're rational. And notice that there, the degree of k of x is minus 2. And it turns out that implies that the degree of minus k of x is 2. And so it turns out that on a Riemann surface, the ampleness criterion just boils down to the degree positive or negative. So here, this is where the anti-canonical class is ample. And of course, what do we call G equals 1? That's our friend elliptic curves. So the degree of the canonical class is 0. And so that's, that says it's a very different kind of beast. And then what's the term when the genus is strictly bigger than 1? So those are the curves of general type. It's a polite way of saying we don't really know much. And but notice that here, the degree of k of x, because G is bigger than 1, it's positive, so the canonical class is ample. So in fact, one way to think about this basic classification of curves is it's the behavior of the canonical class. And it turns out that when you do the minimal model program, in general, the canonical class is a really big deal. And what we're going to do tomorrow is give a beautiful formula for the canonical class of a toric variety. And if you think about it, toric varieties are, they're basically sort of analogs of this. So it's not quite going to be that minus k of x is going to be ample. That's actually pretty rare. But we're going to see that there is a nice formula for the canonical class. So that's a place to stop. So we will resume tomorrow at 9:30.